Okay, we're gonna go ahead and get started. Nice to see all the Gerdes faces. So it was excellent. We have no one here. Yeah, there you go. Anyways. I'm Charlie Nielsen. We have a few other. After our guest speaker. This is the first meeting of 2025 at the University of Lowbrow. In fact, it was funny. I walked in, I told Austin, I go, yeah, come on. Yeah.
You got, yeah.
Yeah.
You got your mic on?
No.
That's what I was wondering. We
I actually don't use
You can use one of these.
probably.
Okay, right. Yeah.
Hello.
There we
You're
go.
on.
Equal word.
I think so. Anyway. So I'm Charlie Nielsen, the president of the club, have been for a long time. We got a few other officers here. We'll get reports on that after our guest speaker. And you have found your way, obviously, into the first University of Lowbrow Astronomer of the Year, meeting of the year. In fact, this morning when I walked in, I said to Austin, I goes, "What we just heard like a week?" He goes, "No, it was last year." Thinking of it that way, but yeah, they come around faster all the time. So anyway, our speaker tonight is actually a return of a speaker we had back in December, I think it was, of 2023. So it's been just over a year. And that is Professor David Gerdes. He received his Bachelor of Arts in Physics from Carleton College and his Master of Advanced Study in Mathematics from Cambridge University, as in the one in England. After receiving his PhD in physics from the University of Chicago, he came to the University of Michigan Department of Physics in 1992 as a research assistant, where he was part of an experiment team that discovered the top quark. He joined the physics faculty in 1998, and he also holds an appointment in the Department of Astronomy. A gifted educator, Professor Gerdes has received numerous University of Michigan teaching awards. He served as a physics associate chair for undergraduate education from 2016 to 2019. And on January 1st, 2019, he became the chair of the University of Michigan Physics Department. And I just discovered moments ago that is no longer true. As of 17 days ago, he is not the chair, but that's because he is about to become the Dean of Science at Chase Western University in Cleveland. Congratulations. Except that he's leaving us, but we'll forgive him.
I am retiring from Michigan. I'm not, quitting. So I will still be a professor emeritus at Michigan.
Oh, excellent.
Yeah.
Excellent. Very cool. So a little bit about his talk tonight. The solar system beyond Neptune is home to thousands of small icy worlds that represent preserved remnants of our solar system's formation and early evolution. Because they are so distant and faint, they are also extremely difficult to detect. While the first trans-Neptunian object, Pluto, was discovered in 1930, the second was not discovered until 1992. Using large telescopes on the ground and in space, and aided by the tools of modern data sciences, David's research group has discovered hundreds of new trans-Neptunian objects, including a Michigan-sized dwarf planet over 3 times Neptune's distance from the sun. Many of their discoveries are too faint to be seen in individual images, but emerge when the images are combined in a way that matches the object's unique rate of motion. Tonight, he is going to take us out there beyond Neptune in a presentation titled "What's Beyond Neptune? Search and Discovery in the Kuiper Belt and Beyond." I do know one thing up front. If we were out there, we probably wouldn't be complaining so much about the cold here. Maybe next week or John, but still. And again, as I had mentioned, this is our return of David Gerdes to us. So after that first experience, he actually came back.
Had me back.
Very much and appreciate it. And with that, Professor David Gerdes.
Okay, thank you so much for that generous introduction. And it's great to be back. It's nice to see many faces that I remember from a year ago when I came to tell you about the solar eclipse. My talk tonight is about what I do with my, actually in my research. Eclipses are a hobby. I normally point my telescopes in the opposite direction of the sun, towards the Kuiper belt, and I want to tell you about that tonight. It's nice to see so many people in lowbrow astronomy gear, but shout out to the guy in the back in the lion sweatshirt. Go Lions. All right, so I've shown on the front slide, so I can just acknowledge right away the support of the funding agencies who support this work. We are supported by NASA and the National Science Foundation and my many really talented collaborators and students at Michigan and elsewhere who have helped make this research program what it is. So I want to start with a sort of high-level perspective on how discovery and innovation is intimately connected with technological progress and advances in instrumentation. So for thousands, I mean tens of thousands of years, the only tool we had to study the night sky was our own naked eye. And it was not until relatively recently, in historical timescales, with the invention of the telescope, that we could access features that our eyes cannot see. And it immediately, when Galileo turned that telescope from things on the ground to things in the sky, immediately it became apparent that there was a whole world out there that we just didn't know about before. The moons of Jupiter, the rings of Saturn, the phases of Venus, spots on the sun, craters on the moon. None of this was apparent to naked eyes and suddenly became, very clear. And so it has been the case ever since Galileo that every time new forms of instrumentation have come along, larger telescopes, photography, digital sensors, CCDs, we have, as well as new regions of the electromagnetic spectrum. There's also visible light that was also our only window on the universe for most of history, but then infrared astronomy came along, radio astronomy, X-ray and gamma ray astronomy. Now neutrino astronomy and gravitational wave astronomy are added to our array of ways to access the universe. But when it comes to the solar system, so let's look at what this has meant for the solar system. So here is a chart spanning a couple of centuries on the x-axis, and on the vertical axis we have the estimated magnitude at discovery of solar system bodies. So I think you all know the magnitude scale, and it's kind of crazy that bigger numbers mean fainter things. You probably also know that it's a logarithmic scale, so that each difference in one magnitude is a reduction by about a factor of about 0.4 in flux. Uranus is just about at the very threshold of naked eye visibility. There may be times of its orbit and very dark locations on Earth and great seeing where you could possibly see it with your eye, but nobody ever did. Nobody ever noticed that that was a planet until telescopes came along. And then with the invention of the telescope and its use as a research instrument in astronomy, a few minor planets were discovered in the 1800s, and Neptune was discovered in the middle of the 1800s, followed by a whole sequence of fainter and fainter minor planets. Originally, actually, these objects, it's like Pallas Vesta series, were considered new planets. And Neptune was another new planet. And pretty soon after all these things started coming along, people realized that maybe this is a different type of object, that there's thousands and thousands of these things between Mars and Jupiter, and maybe they're not really planets. We need a different name for them. And so they were called asteroids, which means they look like a star. and the stella and asteroid is kind of the same root word. And so the pace of that discovery accelerated when eyes started being superseded by photographic plates. In the late 1800s, you could take longer exposures. Film is more sensitive to light over long times than our eyes are. Film eventually got better. And you could easily compare images of a region of the sky at different dates. And you could see that objects moved or appeared and disappeared. There was a pause during World War II when nobody did astronomy. And then deep surveys started coming along, especially the Palomar survey led to many, many discoveries, not only in solar system astronomy, but in extragalactic astronomy and so on too. And then finally, with the development of CCDs starting in about the late 1980s and really coming into their own in the 1990s, around the time I came to Michigan, the pace of discovery really, really accelerated because digital devices are much, much more sensitive to light than the best photographic film. And of course, telescopes were getting bigger and better at the same time as well. And we continue to see these kinds of advances today with instruments like the James Webb Space Telescope that can see infrared light from the beginning of the universe and free of atmospheric obstruction, and it's a great tool for all kinds of astronomy. I've noted one particular object up there, Arrokoth. It's the faintest object on this graph, and that is a special trans-Neptunian object that has actually never been observed from the ground. It was discovered and has only been observed by Hubble, but that is through an intensely targeted effort to find a post-Pluto target for the New Horizons spacecraft, and that's the object that was flown by New Horizons in 2019. So, we tend to think of the solar system as the sun and 8 planets, or if you're of a certain age, 9 planets. And many of you remember when Pluto was a planet. But there's a lot of stuff out there, and that's what this talk is about. In fact, they fall into various population groups, and the largest of these groups is that. So what are those discoveries as they have mounted over the years? The vast majority are main belt asteroids, the asteroids in the belt between Mars and Jupiter. There is a subset of those called Hildas that I'll maybe or maybe not have time to talk about at the end. Kuiper belt objects. So this very first one was Pluto. And then a long time happened when nobody found any other Kuiper belt objects. But look, when CCDs were invented, all of a sudden the Kuiper belt just flourished. Jupiter Trojans are an intermediate group of asteroids that co-orbit with Jupiter 60 degrees ahead or behind it. Those are targets of the NASA's Lucy mission, which was launched a few years ago, and will start kind of a tour of some of the Jupiter Trojan asteroids beginning in 2027. And we've done some work on that I may also have a chance to talk about. And then we just see in the last couple of years a handful, only 2 are known so far of interstellar objects that were gravitationally ejected from a different solar system somewhere and traveled through the galaxy and briefly flew by us before continuing on their way through the Milky Way. And that you can imagine also rising in some future version of this plot. When future surveys we'll discover more. It's just inevitable. So here they are on a map of the solar system. And what I've done here is I've shown the inner planets out to Jupiter on a linear scale, and then I've sort of compressed the outer orbits logarithmically so they don't fill this room. But you see the near-Earth asteroids there in blue. Maybe there's a laser pointer. You see the near-Earth asteroids there in blue, and you see the Hildas that I mentioned before, that that group that's arranged in sort of a triangle. And the Jupiter Trojans kind of clustered 60 degrees plus or minus from Jupiter. Yeah, there's in red are the Jupiter Trojans. Here's Jupiter leading and trailing Jupiter by 60 degrees. So they share Jupiter's orbital period. The Hildas are they're considered a class of their own because they are in orbital resonance with Jupiter. They orbit the sun 3 times for every 2 orbits of Jupiter. And no, they don't orbit in triangles, but their elliptical orbits kind of collectively fill out that triangular shape. And then you finally got the Kuiper belt out beyond Neptune. Notice that it's not uniformly distributed, and here's a pop quiz. You'll notice that there's sort of some particularly sparse regions down here at around 5 o'clock and up here at around 11 o'clock. And I wonder if any of you can speculate on why that is.
Blind spots in our ability to observe.
Exactly. It's not a physical effect of where they really are, but Kuiper belt objects are primarily located near the ecliptic plane, like everything else in the solar system. And the ecliptic plane crosses the galactic plane in 2 locations, 180 degrees apart, there and there. And almost nobody tries to look for Kuiper belt objects in the galactic plane because it's the hardest possible place in the sky to look. Guess where the New Horizons spacecraft happens to be flying? It's, right because where Pluto happens to be near the galactic plane right now. And these things orbit the sun so slowly that this effect kind of doesn't just wash out after a few years like it would for other population groups. So that's purely an effect of they're in a place where they're hard to find, but in 50 or 100 years, they'll get easier to find. So let's just pause and honor Neptune as the last planet before we move even further out. That is still our best view of Neptune, taken by the Voyager spacecraft in 1989. It is, I showed you on that graph before. It's the first. It is also special because it is the first object to be discovered through mathematical inference. Through a calculation that said, Uranus's orbit is perturbed. It's behaving as though something else is tugging on it. And observations were good enough and mathematics was sophisticated enough in the 1840s that you could use that information to say, look here for something about this big. And they did, and they found it. It's sort of at the geometric mean in mass between Earth and Jupiter. And Neptune is, as we kind of gauge distances in the solar system, if Earth is 1 astronomical unit from the sun, 1 standard unit of measurement in the solar system, Neptune is 30. So we kind of think of 30 AU as the end of where the planets live and the beginning of this 3rd zone, the Kuiper belt and beyond. The terrestrial planets, the rocky planets, then the giant planets, and then beyond Neptune, the trans-Neptunian solar system, where the Kuiper belt lives. At one point, there were 9 planets. Now we say at one point there was Neptune and the first Kuiper belt object. And it's fun to go back and look at how this was reported back in 1931 in the New York Times. The 9th planet is discovered. It had been only 84 years since Neptune. I mean, like, people could have remembered Neptune and then Pluto. But notice that initial reports suggested it was possibly larger than Jupiter. This is all to say, like, don't always believe what you read in the newspaper, especially about very recent discoveries. And it wasn't long after that, and this is really interesting to me, that this kind of debate about, is it really a planet, started to wait a minute, it's not actually larger than Jupiter. Doubts have been raised whether it's really the 9th planet, because its orbit is weird. It's now thought it may be proved to be a unique asteroid or an extraordinary comet-like object. And they go on to say, the orbit is weird in the following way. The orbit is very eccentric. It's actually not that eccentric, but so they're wrong about that. But they do get the inclination right. In fact, it turns out, and I kind of stumbled onto this fact myself when I started doing this, that inclination is one of the first things you happen to measure very well, and eccentricity is one of the things that you don't measure very well, because it's very easy to measure the kind of motion across the sky, but eccentricity is about how it's moving toward and away from you, and it takes longer to detect that. So how did they do it? So everybody's heard of Clyde Tombaugh sitting at his telescope. In fact, he died on this day in 1997 at the age of 91. So they took photographic plates, and here was one on January 29th, and here's one about a week later, and there's a dot there. And if you look a week later, that dot is not there, but there's a new dot over here. And the arrows, of course, help you do that. But if I didn't put those arrows there, we could all probably sit here a pretty long time before we figured out what's different about, like those pictures you used to look at when you were a kid, like what's different, and, find 7 things about these 2 pictures that are different. And, the dog has 3 legs. And so imagine the work it took to scan hundreds and hundreds. This is a small region of 1 plate, and there were hundreds and hundreds of these plates. He used a tool called the blink comparator that used you could put these 2 plates side by side in a machine, and there was some eyepieces you could look through with a mirror that would toggle back and forth between the left image and the right image. And when you do this rapidly, you see that the stars don't move, but you can see a dot jumping from left to right and back again. It motivates you to think if there might be a better way to do that. And of course, Tombaugh didn't have access to computers, but this is basically what we do in a very digital way. We teach computers to recognize differences between things on different nights. And finally, before we leave Neptune and really enter the trans-Neptunian solar system, I want to remind you of this very famous picture taken by the Voyager spacecraft, sometimes called the pale blue dot photo. Out at 40 AU, the sun shines with less than 0.1% of its brightness here on Earth. It appears very small. It's just kind of a slightly large, fat star. Earth is lost in its glare. These are just these things that look like rings are just artifacts from the camera pointing very close to the sun. It's glare from the sun. So it's a whole different world out there. So my own entry into this field, as you mentioned in the introduction, my early work was on particle physics. But so what does particle physics have to do with the outer solar system? The general theme of my research has been finding small, interesting signals in big, noisy data sets using advanced computational tools. And whether it is picking a few interesting collisions out of trillions at Fermilab to find the top quark, or analyzing these images to find these difficult objects, that's kind of what it's about. So the problem sort of appeals to the kinds of research problems that light me up. But in the summer of 2014, we had just started taking data for a new project called the Dark Energy Survey, and that's a whole different talk. But the Dark Energy Survey was a optical survey with the 4-meter telescope at Cerro Tololo in Chile, the Blanco telescope, that was designed to do a survey about 1/8 of the sky over a period of 5 years, is how long it took us to do it. But the goal was to measure large-scale structure and measure cosmic expansion of the universe, to study cosmology. And when we were planning the survey, which took about 8 years to design and plan, we highlighted several projects in cosmology that we particularly wanted to do with this data set. But we said there's also some other science we can do with a detailed map of an eighth of the sky. And we enumerated a whole bunch of things like Milky Way structure and galaxy evolution and star formation and lots of other. Nobody, including me, ever thought of this as a tool for doing solar system science. But there we were in the summer of 2014, and we had the very first 6 months of data, and I hadn't looked at it yet because I was busy, teaching my class. And but it was summer, and I wanted to get my hands on the data, and I wanted to do it in a way that would be kind of fun and educational for me and these two students that I had come in to work with me for the summer. And as a teacher and mentor, it can be hard to find summer projects for students that are kind of right-sized for them. You don't want to give them something big and complicated because either they won't make progress on it, or other people who are more advanced are doing much more. You want it to be fun and educational for everybody, and you want it to be okay if it doesn't work. And so I thought about this, and I realized that we had a set of data that was taken to try to search for type 1a supernovae, which are a cosmological probe. Again, that's a whole nother talk. But the way you find those things is you take pictures of the same field on the sky once a week for 6 months, and you compare images taken at different times, and you look for what's changed. And eventually you see that in some galaxy over here, there's something bright, and that's a supernova. Sounds a little bit like the process for finding solar system objects, right? You're looking for images at different times and you're looking to see what changed. And so that was pretty much my thought process. I was not a solar system astronomer and didn't even try to play one on TV, but that was the thought process. And so I thought, let's use this same data and just look for things that move instead of things that changed in brightness. Let's look for things that just were in this place one time on this one night, and then we never saw them there again. And let's see if we can connect the dots and see which things are the same thing that is in different places at different times. And we will do that by fitting, right ascension, declination, and time to an orbit. And I needed to learn how to do that. So these students came along, and we spent the summer figuring out how to do that. And by the end of the summer, we had found 5 new trans-Neptunian objects in these hexagons, or the fields we were searching for supernovae. And so each of those curlicue shapes is the trajectory on the sky of these 5 new objects, and the red dots correspond to times when we saw them. I'll just pause and say a little bit about why those shapes are what they are. It is a combination of 2 different motions. There's the intrinsic orbital motion of these objects as they go around the sun, but we're observing them from a moving platform that's going back and forth plus or minus 1 AU over the course of a year. And so there's parallax. And so we're seeing it's the same parallax that causes Mars to be retrograde and then prograde as we pass it on the inside track. So they all have the same general shape, but the details are what tell you what the orbital parameters of these things actually are. And here's one of those objects. There's our version of the blink comparator. It's just looking at this thing on 2 different nights. Yeah, right. So the question is, how do you do it? Well, I'll tell you a little. I won't tell you everything about how we do it, but I will. So I'll get to that, and I'll get to that more in the context of, you think this is hard. How about the ones that are too faint to be seen in any individual exposure? So that's where where we've kind of gone with this. So this was a summer project with me and 2 students, but I'm kind of the things I've done in my career, I'm most proud probably of this program because I think it wouldn't have happened if we hadn't taken it on, because this survey was a bunch of cosmologists, but it turned into a really successful program. In fact, one of the best solar system surveys, of any survey. So we ended up, years later, with hundreds of new solar system objects at a range of semi-major axes, and weird things like an object with a semi-major axis of 450 AU and an inclination of 54 degrees. What is that thing? You know, it's a dwarf planet-sized object, and you know, we found here's the aforementioned Michigan-sized dwarf planet. I will talk a little bit about that in a moment. We also found the largest comet ever found, this giant Oort cloud comet that's on its way in. A whole bunch of stuff. It's a whole program. And you see actually some of these objects piling up at specific values of the semi-major axis. Like here's a bunch of stuff at 39 AU. 39 AU is Pluto's semi-major axis, but there's also a lot of other Pluto-like things out there. Why is that? Well, you've all seen pictures, I bet, of Pluto's weird orbit, which crosses Neptune's orbit. And if you were like, you know, 8-year-old me, you looked at that picture and you said, why don't they ever hit each other? Part of it is that 17-degree inclination, but the other part of it is that, you know, we mentioned the Hilda's in a 3-to-2 resonance. Pluto is in a 3-to-2 resonance with Neptune. That means it makes 2 orbits for every 3 that Neptune makes. And so it always crosses Neptune's orbit when Neptune is in a couple of specific places. You know, it's like gears that match, and only these certain gears teeth will interlock. And so whenever it crosses Neptune's orbit, you're guaranteed Neptune's never there. That's why they don't crash into each other. It is a way for objects to find a stable orbit in the presence of a giant perturber like Neptune. So let's talk about our dwarf planet, because this was super fun. So it is officially known to the world as 2014 UZ224, but we called it D. It's not eligible to be named yet for reasons that are too obscure to go into, but as we started studying this object in our data, we kept calling it the distant dwarf planet candidate, and the distant dwarf planet candidate this, and the distant dwarf planet candidate that. And we finally decided we need a name so we can stop writing the distant dwarf planet candidate in our Slack channel every time. So we called it DD for distant dwarf. So these are images taken, you know, a few weeks apart. And again, you see this little moving arrow. You know, the short answer to your question is it's a complicated combinatorial problem to find. You know, you subtract out the stationary stuff, but then you have a long list of things that were only in one image on one date, and a lot of it's junk. But the constraint that it has to be moving in a solar system-like way, you know, consistent with Newton's laws and Kepler's laws. Yeah. I mean, you know. Well. I just mean it's got to be sort of obeying F equals ma, you know, around the sun. So I mean, like you know that if you have 2 points there and there, you can't look for a third point here. You know, the rate of motion has to be pretty constant, et cetera. So I mean, there's ways to be clever and reduce the combinatorics, but yeah. Well, I'll show you. So this is kind of what it looked like. So if I press go, you will see each little gray dot that comes in is going to be one single detection of a transient, like a thing that was in that image, but not in any other image at that location. So a thing that we could possibly consider as a candidate for including in an orbit. So here it goes. Oh, this is the trajectory of DD. And then here come the observations from DE-CAM. And the red dots are detections of DD by our survey. So now it's the next season, and we have a few more hits. And we go around the sun again. It's the next season, and here come a few more. So there were, we looked at 15,000 images, 1.1 billion little gray dots that might belong to something. 1.1 billion detections altogether in those images, stars, galaxies, of which 5 million were only seen in that particular image at that location one time. So that's a possible transient. So it took 300 computing years to solve this problem. And fortunately, we had more than one computer. So it didn't take us actually 300 years, but it took us a lot of time. You know, if you just erase everything else on this plot, but those red dots, you know, you would not necessarily fit that shape to that, you know, computers are great. So that was 12 detections out of these 5 million transients belong to this. And it's faint. It's a 23rd magnitude object. That's like seeing a candle halfway to the moon. This particular object takes, you know, it's 90 AU out there. It takes over 1,000 years to orbit the sun. So we got excited about this, and the reason we got excited about it was because you know, we immediately realized it was 92 AU away, and the only thing at the time that we knew of that is further away than the sun than that is the dwarf planet Eris, and which is a Pluto-sized object. And so if you plot current distance from the sun versus you know, a number that roughly translates into a size, you know, this thing was potentially quite big. It's out here with Eris and Sedna. You know, Eris is really bright, but we didn't know exactly how big. And the reason we couldn't know exactly how big is that we're observing it in reflected light from a, you know, with the optical telescope. Just we're seeing reflected sunlight, and we don't know if what we're seeing is a small shiny thing like a snowball or a disco ball, or a big dark thing like a lump of coal or something in between. They all look the same to a telescope. But they don't look the same in the infrared, because the infrared, you know, sees heat, and heat is proportional to size, right? You know, large cold objects give off more heat than small cold objects at the same temperature. So if we could observe this in a different region of the spectrum, because of the technological innovation of submillimeter astronomy, we could break this degeneracy between size and reflectivity, which is called albedo. So we wrote a proposal to the director of the ALMA Observatory, a submillimeter observatory located in the high Atacama Desert in Chile. Now, time on these instruments is highly oversubscribed, and it is awarded through a competitive peer-reviewed process about, you know, 6 months to 18 months in advance. But they reserve about 5% of the time for what I would call matters arising. And so we wrote a short proposal to the director of ALMA, and we said, we would like to use some discretionary time that you have as available as director to observe this thing that we found. We think it might be big. Can we please have about 12 hours of time on your $1 billion instrument right now? And they thought about this for like a week, and they said, okay. And so my students I had more summer students by then, and they got a completely wrong idea of how progress in science actually goes. You know, this thing went from like a, you know, line in a table on our laptop to we're pointing ALMA at it in just a little over a month. So they said, sure, but here's the deal. We don't know when we're going to be able to take this data. We're going to fit it in, you know, as we are able. And so we need you to give us a table of you know, positions of this object at 2-minute intervals for the next 3 months. And they call this an ephemeris. And make sure to correct for the rotational parallax of the Earth at the location of the ALMA Observatory, because, you know, the field of view of this thing is so small that it matters that this thing is on a mountain in Chile that might be here or here as the Earth rotates. So I did all this. You know, there's tools to do it that I didn't have to invent myself. But, you know, I hit send, and I was so nervous that they would point their $1 billion instrument at the wrong spot, and I'd get, you know, a beautiful picture of a blank piece of sky. But So they took this data right away, and thankfully, I didn't screw it up, and there is the heat from Gerdes. And based on how much extra flux is in this region of the image, we were able to infer the size of Gerdes and figure out that it's 635 kilometers in diameter. It reflects about 13% of the light that it receives, so it's like dry dirt. And it's not dry dirt, but that's what its albedo is like. So it's a pretty big thing. It's probably in the top 24 largest objects in the solar system that aren't a planet. It wasn't, the 1,000-kilometer object we might have hoped for, but that's still pretty big. So there is Pluto, and there's Gerdes, the Michigan-sized planet. It's kind of a Sharon-sized, object. Okay, so I'm not going to get to talk about Hilda's, but I do want to talk about how we have extended these ideas of connecting dots to building an object out of images that have no visible moving dots. So here's the way that you traditionally find KBOs. You say there's a moving dot, and you connect the dots. Notice how starry this image is. This was data taken from as part of a New Horizons target search, and I told you that's a terrible area of the sky to look. This is why no one looks for KBOs in the Milky Way. But we found that one, and just fun fact about that object is we found it here at Michigan, and New Horizons observed it about a year later, and that's what it looked like from New Horizons from 1 AU away instead of 50 AU away. And at the time this image was returned from the spacecraft, it was the most distant image ever transmitted back to Earth. This was a record that stood for a couple of hours until New Horizons sent another image back. It's getting further all the time, but still. Okay, so now let's think about how you could go even fainter. Think of that image with the moving dot. What about the things that you can't see in that image? How could we try to pull them out? So the analogy I want you to think about is when you're trying to photograph a moving object with kind of a slow shutter speed, like a sprinter, or a race car, and you set your camera on a tripod, and the thing zooms by, and the object is blurred, and the trees and stuff in the background are stationary. But you've probably seen photographs where the photographer panned the camera at the rate that the car was going by. So you see this nice sharp picture of the car and all this blurred stuff in the background. That's what we would sort of want to do to capture moving objects like this in a long exposure. And normally in astronomy, the way you go fainter is to do longer exposures. But you can't do that with moving objects because they just move on, and then those pixels that it vacated start filling up with background light, and so they wash out. But if you could pan the telescope, if you could track the telescope at the rate of the moving object, the stars would streak, like the trees in the background of the race car. The stars would streak, but the object would just stay there in the same pixels on your camera and get brighter and brighter the longer you expose. So that's the idea. You see in this is a simulation, but you see these various moving objects here that this one's a bright one. It's making a long streak. These are, it's hard to tell what those things are. And then there's a star there at the center that's getting brighter as we expose. So here's but the problem with naively just moving your telescope at a different rate, well, there's two problems. One is you don't know what rate to move it at because we haven't found the thing, and they're moving at different rates. The other problem is that there could be multiple such objects in the same field, all moving at different rates, and why pick one? Let's try to do them all. So here's our technique. We take many short exposures. By short, I mean like 2-minute exposures, and we do 100 of them in a row over a period of several hours. So here is something like that. And, you see the same star. We put those all together in the usual way, and it creates a template image with any prospective faint moving objects, presumably, washed out. But there's a template image. Then we subtract the template image from each of the individual images. That is a way of getting rid of all the bright stationary stuff. So now they're all, in principle, kind of blank, except if there was a moving object in any of these images, some small number of pixels are some tiny fraction of brightness units above the background, but nothing that you would notice in any one image. But now that we've got these images, we can kind of virtually start to pan the telescope at a whole bunch of different rates just by shifting each image before we add it at a different rate. And so we can do that at any rates we want. We can pick every rate that corresponds to a physically achievable motion of a solar system object. So that's what we do. And so here is, as this goes by, each point in this grid represents a different X and Y rate of shifting each image before we add it to the stack. And so as we do that, you see these like different objects kind of coming into focus when we combine the images at their rate. So there's kind of one up there. And as we get like close but no cigar in the right rate, you kind of see it elongating and in some way that represents how you were off. So that's the idea. Of course, this is extremely computationally intensive because you're making, roughly 100 copies of the same set of data, doing searches for point sources in each one of these things, and also getting 100 copies of every piece of junk in every image. So the signal to noise is super, super low. But that's what we did with our with a follow-on survey that we did that was, unlike the dark energy survey, a purpose-built. What just happened? The screen fell asleep? It's on my laptop. Let's. Okay. Oh, but room. Well, I don't know why my.
We can see that.
But room PC, yeah. It'll show the. Okay, it's not ideal, but I don't know why my.
It's got to be something disconnected.
I don't know. Well, I don't know. Anyway, let's. This is all good. So we got 47 nights on the same telescope, the 4-meter that we found that we did with DE-CAM to do these 4-hour sequences. So it's much deeper over a much smaller area than 1/8 of the sky, like we did with the dark energy survey. But the idea was to go really, really, really super deep and find the faintest Kuiper belt objects ever seen kind of at scale from Earth. I'll skip our papers and so on, but I do want to talk about this work of the shift and stack. So here's how we sit in comparison with other surveys. And there's always a trade-off in astronomy between area and depth. You can go right over a big area or faint over a small area. So we are about 100 square degree survey that reached 26th magnitude, and that compares to previous and planned surveys. It's kind of the deepest bang for the buck, so to speak, of any survey. And those contours represent the size of the blob there represents kind of how many TNOs you might expect to detect. So we did it over 3 years. We started with a smaller field, and then we expanded the survey area as the original group of objects started to diffuse. 2020 was a complicated year, as you may recall. We have 4 groups of fields like this at different locations of the sky. This particular field grouping was the only one we were able to observe in 2020 because by October and November, when these fields were visible, the observatory had reopened, but only for remote observing. So we were able to complete the survey for that field with 2020 data. So the real grid that we used isn't a box. It's kind of this ice cream cone shape that covers the full space of bound orbits beyond 30 AU. So at each of those dots, we form a combination of those 100 images. We search for point sources. If we find one, we do some finer stepping around the candidate rate of motion to really zero in on where it is. So the color here represents signal to noise. So high signal to noise is good. And usually that when signal to noise is high, it means you've really put all the light in the smallest possible spot. And so this plot shows on the right the best rate of motion with the highest signal to noise at the center, and then all the nearby rates. And you can sort of, this one's a faint one, but you can see it kind of elongating, as you start to deviate from the best rate of motion. This is a fake object that we implanted into the data. And a really important part of our quality control is to salt the data with these fakes in a blind way, and run all the same codes on it and see, which ones do we find, which ones do we miss. And it helps us to understand what we're really detecting. So this is a 27th magnitude object. It's 3 billion times fainter than the naked eye limit. With a 4-meter telescope, it's pretty incredible. So these two, there's a lot of information here. These 2 squares in the inset show on the left what you get if you just add those images together in the normal way without shifting them at all. And so this is showing that this object gets washed out because it was moving and we blurred it out. But when we follow it at the right rate in software, we see this object emerging at about signal to noise of 7 or 8. So here's how it goes when you combine them. The one on the left is pretty bright. It's relatively speaking, it's 25th magnitude. The one on the left is the bright one. The one on the right is the faint one. Now, this 25th magnitude one looks like a searchlight in this rendition, but that is much fainter than the single exposure limit of the dark energy camera. None of the things we found with the dark energy survey were anything like this faint. So we're really, really pushing this telescope to its limits. So here's some details. That's after the subtraction of the template image. I told you it's a computational nightmare, and it's because there's a lot of just real junk in these images, and most of the things it thinks it finds don't look anything like solar system objects. So we use artificial intelligence, neural nets, image processing to try to filter out the round things. That's still not good enough. And so we have a second convolutional neural net that looks for that kind of radial pattern in the set of images at adjacent rates to see if it's like deviating from round in a way you would expect if you were close, but not quite right. So it's looking for this pattern, and it's trying to reject these kinds of patterns. That was still not enough. Well, now it's enough. Our neural nets have gotten better since then, but we finally had people, me and students and volunteers, my wife, looking at these images and kind of flagging them as good or bad by eye. So the existence of those fakes that we put in there allows us to, kind of see when we stop recovering them because they get too faint, and it's different on different nights. The seeing is better and worse. So each curve is a different night. But we went, way deeper than any previous survey. And even this future legacy survey of space and time with an 8-meter telescope using single exposures won't get nearly as deep as us. That's still not enough to really understand what you're doing. And so the last step in this very complicated process was to do the whole thing over again, but to do it at flipping the rates of the shifting and stacking. So like if the sprinter's going that way, we went this way. And at rates that no physical object could yield a signal. And that means that anything you find, or your code thinks it finds, or your observer, your inspectors think they find, is a false positive. So that gives us kind of a number that we need to subtract from everything we found. Like this thing here. I mean, it looks pretty good, right? This would probably fool me, but it's a, and again, when we showed this like on the website to our human inspectors, nobody knew if they were looking at a reverse stack or a forward stack, and nobody knew if it was a fake or a real thing. It was all blinded. But when you combine these things, the forward and the reverse, you see that in the forward stacks, there's this whole blob of stuff here that's not present in the reverse stacks, and that's the Kuiper belt. You subtract this one from that one, and there's the Kuiper belt. Oh, because you're looking at millions and millions and millions of image combinations, and sometimes statistical fluctuations just produce a source that looks pretty round. These neural nets, these algorithms are not perfect, and when you're looking at signal to noise of 5, I mean, it's a question of how low do you want to go. Most of these things in the reverse stacks are quite low signal to noise. If you find something at signal to noise of 20 or 30, it's real. But the whole point of this was to push it as low as you can, into the statistical noise. And so you want to, so it's a kind of different way of thinking about these discoveries. Instead of saying we found a thing or we didn't find a thing, we associate a probability with each discovery based on the false positive rate at that brightness. We say, there is an 87% chance this thing is real, and it gets kind of weighted accordingly. So you put these all in a table, and you see some type of message emerging. So that's 2,300 KBOs. I was excited that first summer when we found 5. We've come a long way. In context with the history that preceded it, our survey, I need to take the word projection off here. We wrote this in a proposal, but we did it. So we're kind of up here. Now in the second half of my talk, I think I'll stop there. And I could tell you more about Gerdes and Jupiter Trojans, but that's kind of a separate research thrust. So I think I will skip ahead to my conclusion, which is that it's a big solar system out there. With the right tools, you find new stuff every single place you look. And point a mirror. Not working again. I'm just curious. I don't know why it's done that, but so what we are doing now, besides continuing the Kuiper belt work, is applying these same shift and stack techniques to some of the nearby populations, the Jupiter Trojans and the Gerdes. That's more challenging because they move faster. They're much closer. And so you need to combine the images at many, many, many more rates. Instead of 100 rates or so for the Kuiper belt searches, it's more like 40 or 50,000 different rates. And so we have had to further optimize these tools to run on GPUs and, train smarter neural nets and so on. But where that's going is if we could extend this work to find ultra faint Jupiter Trojans and Hildas, if we look in the right place, we might find more targets for the Lucy mission. And so we're exploring those possibilities now. The Lucy mission, which is the mission to the Jupiter Trojans, is visiting, I think, 4 or 5 targets at L4, but only 1 at L5. And wouldn't it be nice if there was another target at L5? And it's not getting to L5 until 2033. And so we've got some time to do that. Maybe even a dean has time to look for Jupiter Trojans between now and 2033. So I'll stop there and take your questions. Yes.
You covered this at 100 square degrees.
Right.
Well, if you take the 300 multiplied by 400, there's a lot of stuff.
There's a lot of stuff out there. Well, you don't quite multiply it by that big of a number because they're not uniformly distributed over the sky. But what we did do was take the ones we found. I might have glossed over that. But there's one of the slides I skipped. But what we did was we in that paper I highlighted, we took the number of objects we found. We took their brightness distribution, from which you can infer a size distribution, and some things about the density of these objects. So we can sort of, in that block M I showed you, we kind of know what the total mass of that stuff was. And then we can multiply that by sort of a function that represents what fraction of the Kuiper belt that is, and get the total mass of the cold classical Kuiper belt, the kind of low inclination, very circular stuff at 40-ish AU. And it works out to be about 2/10 of an Earth mass. So there is a lot of stuff out there, but it doesn't add up to much.
These things being big enough for the influence for them to see.
Yes, absolutely. So another thing I didn't talk about was with what? And do spectroscopy. Oh, I wish I brought a plot. You should join my team. So we as part of our dark energy survey work, some of the things we found were Neptune Trojans, which are like Jupiter Trojans, but they're associated with Neptune. And there's a curious issue with Neptune Trojans, that there aren't as many red ones as you think there should be. There are kind of some red ones and some blue ones, but more blues than reds. And they are thought to come from the Kuiper belt, but the color distribution was wonky. So we wrote a proposal for the very first James Webb proposal cycle that was open to the community to do infrared spectroscopy of Neptune Trojans with James Webb. And we got these beautiful, beautiful infrared spectra that, like they were so good, they looked like the simulation we put in the proposal. And we found that this red one is quite spectroscopically different from its companions out there. We can, based on this is reflection spectrum, so there's just like what holes show up when the sunlight that don't get reflected back at you, and what could absorb that color. And we think it's a combination of methane ice and CO2 ice and a little bit of water ice in some of them, and which adds to the belief that like water was delivered to Earth from the Kuiper belt and from comets, and then like kind of organic goop that's called tholins that gives it a sort of darker color. So exactly, but you cannot do that kind of spectroscopy from the ground because the sky is very bright in the infrared. That's why Webb's in space. I saw a question over here. Yeah.
I was going to ask what the total mass was of all this stuff that you would find.
Yeah, so the cold classical Kuiper belt is about 2/10 of an Earth mass. The more excited, when I say excited, I mean like higher inclination, more eccentric, kind of they've had more dynamically interesting paths than these just undisturbed objects in the cold classical belt. That's about another 3 or 4 tenths of a percent of so that's even Pluto. I mean, like Pluto's not big. It's a tiny fraction of an Earth mass. So all together out there, it's just a fraction of a percent of an Earth mass. Oh, the main belt. I don't know. I should know the mass of the main belt. It's less than the mass of the Kuiper belt. Although there are a million known asteroids in the main belt, they're all way smaller than Kuiper belt objects, just because we can see them from here. Of course, there are 5-kilometer Kuiper belt objects too, but they're not detectable at the moment. Yeah.
How many comets?
I personally have not found any comets, but the Dark Energy Survey, my collaborators, an analysis that my collaborators, Gary Bernstein and Pedro Bernardinelli at Penn led, doing this connect the dots exercise in a different way than we did. They found comet Bernardinelli-Bernstein. You can look it up. It is a giant, like 300-kilometer size. I think it's that big. Might be misremembering it, but it is a huge Oort cloud comet that's come in from 10,000 AU. It's almost certainly never been here before, but it's showing signs of cometary activity at like 25 AU. It will reach perihelion in 2031 or 2. Unfortunately, its perihelion is only like 10 AU or something. It's not, or 7 AU. It's not going to get that close to the sun to get really bright. It will always be a telescopic object. I mean, it would be awesome if it was like, going inside Mercury and it would be like you could see it in the daytime, but it won't be that bright. Yeah.
You mentioned, I think, the orbit of it takes 1,000 years. Yeah, what's the absolute speed of these objects to the outer?
Well, yeah. So if they are in, D is in a very elliptical orbit, so it depends on where it is in its orbit. It's moving faster when it's closer to the sun and spends a lot of time out at aphelion, moving very slowly. They are moving at a typical distance. They're moving at around 40 kilometers a second, I think. 20 to 40, if I have it right. I tend to think not in terms of kind of absolute units, but in terms of a rate of motion on the sky, since that's what we directly measure. Typical Kuiper belt objects at Pluto's distance are moving about 3 arc seconds per hour. Main belt asteroids will be moving 40, 50 arc seconds per hour. Near Earth objects are moving much faster than that. DD was moving 1 arc second per hour, which is why we knew right away it was, we knew right away it was very likely to be distant. There was always the possibility that it was a much closer object moving on a line of sight very close to us, so its projected motion was small, but we almost never see anything moving. It was far slower than anything we'd seen before, so we thought it's probably pretty far away. Yeah. 1 arc second per hour is, hard to, your backyard telescope probably can barely resolve a binary at 1 arc second, right? Yeah.
So I had to step out for a while, but we read in the astronomy magazine something about a planet 9. Approaching. Can you say something about that?
That's a whole nother talk. So say that a lot. So the idea that there is a hidden massive planet in the outer solar system is a recurring idea in astronomy, going back to the discovery of Neptune in the 1840s. And the search for Planet X that culminated in Pluto that wasn't really a planet. So the latest incarnation of this idea is motivated by observations of what are called extreme trans-Neptunian objects. And that's sort of a word that we use to refer to trans-Neptunian objects like the ones I've mentioned that have very long orbital periods, or I think in terms of semi-major axes, semi-major axes bigger than about 250 or so AU. all of these objects are in very elliptical orbits that were not discovered at 250 AU. They're discovered at, 35 or 40 or 45 AU when they're close to the sun and bright enough to be seen. But they do spend most of their time very, very far away from the sun. If you make a plot as seen from overhead of, there are not many of these objects. Now there's about maybe 20 or 25 that are known. But when the kind of Planet 9 paper that you may have heard of was written in 2016, there were like 6 of them, one of which we found with the Dark Energy Survey. So when you make a plot of these orbits, these long elliptical orbits, they are not uniformly distributed on the sky. They're kind of mostly over here. These ellipses are kind of pointing this way. There's a few that are, but like statistically, if you just would like randomly orient a bunch of rather skinny ellipses with the sun over here somewhere, you'd expect them to look like flower petals and not like this. As if something massive might be interacting with them gravitationally to line them up. So there were a couple of scientists at Caltech, very, very good, smart people who worked out what it would take to produce an alignment like this. And they said it could be produced by a sort of 5 to 8 Earth mass planet in a moderately inclined, kind of 35-degree orbit with an eccentricity of about 0.3 or 0.4 and a semi-major axis of maybe 500 to 800 AU. That would be really cool. I mean, that would be amazing if such a planet existed. And so, this was right in the thick of when we were analyzing the Dark Energy Survey data, and we had an eighth of the sky to play with. So we were really excited about the possibility that this Planet 9, which would be bright enough for us to see in single exposures, could be found. Well, we didn't find it. Nobody else has found it. And we started to think about what else might cause these long elliptical orbits to line up over here. Are there observational biases that might lead to a preponderance of discoveries like that? I showed this plot at the beginning of my talk of the Kuiper Belt, and I said there's these 2 holes. Why is that? It's not that there's a planet removing Kuiper Belt objects from that region of the sky. The Milky Way is in the way, so nobody looks there. So is there some kind of analogous thing going on with how we find this particular weird class of objects that leads to that pattern? So my student Kevin Napier and I analyzed so these extreme TNOs have been discovered by a variety of different surveys, some of them quite a long time ago, and nobody really knows how they did it. But we looked at the recent discoveries from surveys that have like fully documented where they pointed and when and what their limits were. And so you can really kind of model their sensitivity and ask yourself, what kinds of things could they have discovered? So we basically ran a bunch of simulations where we filled the sky with these extreme TNOs that were uniformly distributed, ellipses pointing every which way. Ran them through a simulation of each survey's selection function and asked, what are the ones that they actually find look like? They look like this. So, so we wrote a paper. You can look up Napier and Gerdes in 2020, I think it was, and we said there's these things are completely consistent with a uniform distribution and selection bias, and I think it convinced most of the community, other than the 2 guys at Caltech, because the outer solar system makes people a little crazy, and they latch onto an idea that they might have found something really important. But the longer that this thing fails to turn up, the more confident I am that it's not there. It's also, you got me started. It's also really hard to make something like that. A 5 Earth mass planet at 500 AU. Like, how do you do that? There's not 5 Earth masses worth of stuff out there. I just told you the mass of the Kuiper Belt is 2/10 of an Earth mass. So where did 5 Earth masses come from? It couldn't have formed out there. So either it formed close and through a series of unfortunate accidents got kicked out to there, but then it would still be very eccentric. It would still come back in. So you have to circularize it somehow after it gets out there. It's really complicated. The other way you could do it, and it's kind of inventing more magical things, but the other way you could do it is the sun, like most other stars, was born in a cluster. You've all looked at open star clusters, and so these are very young systems where stars recently formed. So the birth environment of the solar system was a much more crowded place than what we live around now. These clusters dissipate after a few tens or hundreds of millions of years. So, but it was possible that in the early history of the solar system, we experienced a flyby from another neighbor of our sun, and planetary material was kind of exchanged in this process, and that there is a way that can lead to weird orbits too. But you kind of say, well, is it this series of kind of weird, unlikely events, or is it observational bias that is readily explainable on the part of surveys? And Occam's razor to me says it's the latter. But it would be great. I mean, we all want there to be a planet 9, and that's why the outer solar system makes people crazy, because if it was there, what would we name it?
Can't be Planet 9.
No, and well, they one of the guys who did it is Mike Brown at Caltech, who discovered Eris and Haumea and some of these other well-known dwarf planets, and he is kind of probably the most prominent figure associated with Pluto being deplatformed, and and in fact, Mike's Twitter handle is it's ironic that it's called X now, isn't it? Mike's Twitter handle is at Pluto Killer. So him calling this hypothetical planet 9 was kind of a poke in the eye of the Pluto people. But if we're so fortunate as for there to be a planet 9 in the solar system, it'll get a real name. And there's rules about that, and that's a whole nother talk too.
Those Caltech guys are speaking here next month.
Are they? Okay. Well, tell them I said hi. We have sort of a friendly rivalry. So.
But the smaller objects don't fit that you've been discovering.
So
do not fit into that.
well, they're not in this sort of extreme category. The vast majority of Kuiper Belt objects, including almost everything we found except for a few, they all stay within about 100 AU of the sun, and so they won't be influenced by Planet 9. I mean, part of what the work that the Caltech group did to kind of come up with the Planet 9 that I told you about was it's got to be sort of massive enough to line up the extreme TNOs on 4 billion year timescales. It's got to be far enough away and not too massive to not like mess up the rest of the Kuiper Belt, which is symmetric. So you've got to make it sort of such that only the things that get really far out there have a chance to have their orbits modified by it. That's why you get 5 Earth masses at 800 AU, and it's only got an eccentricity of 0.3. Any more questions? I know you have some club business to do too, but maybe time for one more. Mhm. So the work I showed, like with those 2,300 Kuiper Belt objects, that was those 3 years of data, 2019, 2020, 21. It was a total of, I want to say, about 2,000 individual images taken of those fields over the course of 3 years, broken down into units of about 100 2-minute exposures on a given night. But then we had multiple nights, so it was the order of a couple thousand images. Each image is 580 megapixels. It's about yeah, it's a lot of data. I mean, it's not like particle, it's not petabytes of data. It's not large language models kind of data, but it's big in terms of astronomy. Yeah, I mean, the work was really optimizing these algorithms so that, if we were to do the DD search today, it would not take 300, because we know how to do it faster and better now. But at the time it was, but so rather it's the case that like what you can do with years of computing time just keeps getting better because we get smarter and computers get faster. No one ever says we just need, a week of computer time now to do this. They say with this now with 100 years of computing time, look at all this other cool stuff we could do that we couldn't do 5 years ago because computers are smarter and so are we. Well, thank you all very much.
Hello, do we have any questions from the Zoom audience?
I haven't seen anything.
No, nobody's hands up. Nobody's unmuting. Thank you very much again, David.
Thank you.
And hey, you can always join us again, even up in Cleveland, we can do Zoom.
It's not that far. It's a 3-hour drive.
Well, that's also true.
Move it down there.
So I'm moving to Case Western Reserve to go Dean of Arts and Sciences, so.
You already buy a house. I mean,
What?
did you buy a house? Move it out.
Yeah,
All right.
well, we haven't bought a house, we're renting. Okay.
I believe we gave you a qualification last time.
I think you gave me a hat. I still have the hat.
Like a shirt matching, or we get you this one? So, well,
I think we'll take the gift certificate.
So we are.
It's Gerdes, my mailing address.
Yeah. Hey. About that. All right. So I just got a couple of things. One of them is we are currently organizing a return to help with pronunciation. Glen.
Sure.
Larry, okay. Elementary school, which is up in East Lansing. A group of us went up, just about, well, it's early February, as I recall. I was unfortunately not able to join them, but I heard the story and it actually went very well and everybody had a good time. So they have asked us to return this time on February 26th. I did send an email about it, and I think we had 6 people, not including myself, so that would be 7, that said they could show. And there's another person that wanted more detail about it. It's possible they will show up too, so we're going to have plenty of people for it. So we've got to, I'll get a hold of our contact there, probably request probably 3 tables. We'll take what might need, so.
Depends on how many people we have to make use of them. We can only set up as much stuff as we can use.
True. Yes, I'll ask them what they plan on bringing, that gives my, so. You're gonna have the C start at that point, Jeff, or?
It should be back.
That's what I'm thinking. I think
Brian's got it
back
checked
with-
out, but I think he said it was gonna be out for about a month or so, but I can email him and find out. That would be,
It would be kind of nice to have that there, yeah.
yeah, probably even set it outside
Yeah.
or show him whatever.
Might even be able to get on those targets that hang up in there.
Yeah.
If they're far enough away. Just like another telescope, something to get on the screen.
Space,
Posted at the.
Yeah.
the place we were in wasn't much small. It was
Oh, really?
small, yeah, width wise, it was about what this room.
Hmm.
So, there's tables on either side with different, science displays. And we set the targets away as far as we could, and those telescopes were able to focus on it. But it was tight.
It was close, okay. Yeah, so if I remember right, the C star does not have a very close focus. I recall, for terrestrial. But still, we can still show it and we can try it. Is there any door we can open and look down the hallway or?
It really, there's a lot, it attracted like 200 kids and their families, so there are a lot of people.
Yeah,
And so the sidelines get obscured.
oh,
pretty
that's
quickly.
true, right.
Here, that, we could get on a chair and put the targets above the foot traffic. So the kids that wanted to were able to do so.
Should we bring a small?
Well, we'll see what we're dealing with. So. And then the other thing I wanted to mention is, we're always looking for guest speakers, and thank you, Don Foley, because he is just, booked, Professor Tarlay, who actually is a U of M professor. I saw him several years ago at Saturday morning physics, and I thought he was quite good. We'll enjoy this. The only thing is that moved to Hawaii.
He's retired.
Yeah, he retired, I think, moved to Hawaii, so. But as it turns out, he actually might be back in town that time. Yeah, you wanna go ahead and mention something? Okay. Yeah, he might be back in town, so the month before that, we should know whether he's gonna be in person. We'll have to do it soon. But it would be kind of half in person, so, but anyway, thank you, Don. So that covers us until April, but we always need more. And that doesn't apply to just vice presidents, anybody. If you know somebody you think would make a good presenter and they're willing to do it, let us know, send it on to them, and that includes yourself. I think all of you would agree that have been around for a while, that some of the best presentations we've had were from ourselves. They really were. I mean, we're club members and relate, so don't consider that, because April will come and be here and gone again like that. So
If you guys are looking for a speaker, get hold of me.
yes, that's right, Jim. Regulars. How many times have you been to? 4 or 5 now? And we enjoyed it.
Yeah, four or five. I've got a couple more that you guys haven't seen. Be happy to. Just
Can we put you
let me
down
know
for
where
May?
you could, where you want to fit me in.
Okay, how about May?
May, what date in May? Well, just have some, May would be fine, I
Okay,
think.
excellent. And since you're there, Jim, I had also sent an email about the sale of McMath-Holbert Observatory. And there's nobody
Yep.
that's more in tune with McMath-Holbert than Jim. If you can send out money more detail if you have it, go ahead.
I can do that. I'm not sure where to plug it in to you guys. There's a major article in the Thursday Detroit News. It's like a 3-page article, front page, that tells most of the whole story about what's going on now.
Okay.
And I could send that to you if you want me to.
Yeah, I can send out the club, or if you just want to send it directly to the club, that's fine.
Okay, nope, I'll do it.
Hey, excellent.
And matter of fact, we could give a little bit of an update on that in May also.
But sure, maybe there'll be some news then. Maybe one of us has bought the place by. All right, thank you, Jim, appreciate it. Okay, Amy, our newsletter editor, was not able to join us tonight, but she did send a report with a simple figure. She needs articles. Please send articles. We actually had some discussion in the office with the group. We even wondered if maybe we should sunset the newsletter. Because it's always a struggle getting articles for it, and printed stuff is kind of maybe going out of style a little bit. We decided that no, we think there's still some value in it. But if we can't keep getting articles, so it's not a newsletter without the articles. So if anybody's got any right about it, we'll send it in. If you mind, I gotta do my annual report pretty soon. That takes a minute. Anyway. Our treasurer, Doug Scoble, did tell me he was gonna be able to join, but then something happened and he couldn't. Maybe I should have just grabbed him.
I've got his email here. We got
Go ahead,
214 memberships. And paid for the AT&T hotline and also reimbursed Jack for the new observatory heater. We're up to 214 memberships.
Yeah.
Maybe I should have kidnapped them and brought them back from something.
Had your chance.
Okay, Jeff.
Yeah, first thing, almost all of the astronomy, the real astronomy handbooks, the brass handbooks, calendars are gone. I think one person hasn't really responded, but for the most part, they're done, but we do have 4 more calendars. And 2 handbooks that are available for purchase, 20 for the calendar, 26 for the handbook, and you can get PayPal to Lowbrow. Or me. We had good success with everybody stopping by and getting stuff or paying the extra money to get it mailed out. I had a chance to try out Club Sea Star. It is a miracle of technology.
Thanks, isn't it?
It is kind of fun.
It's
Yeah.
very addicting, yeah.
Amy is actually the manager, if you will, for that piece of equipment, and we started a quick spreadsheet. And we kind of looked at it, it's like, well, we've got a whole inventory of things the club has to check out. Some need some orientation, training and all that to use before you check them out. We do have a lot of stuff that people don't know about. So I started adding some of the things to the Sea Star spreadsheet as a tab. And then I completely forgot about it, but last year at the January meeting, oddly enough, we came up with a page of kind of guidelines and rules to follow and a sign up sheet that Jack brought to my attention. Thank you. He's got a copy, want to see it, but it's basically collecting your name, address, phone, and kind of common sense stuff. If you break it, fix it, or if you bought it, whatever. It's very straightforward. But the concern is like we got a bunch of equipment that really isn't being used by anybody. If folks want to check out a telescope or whatever we've got on here, approach officers or email the Ask Lowbrows. We'll take care of it. We want to get that list put up on the website at some point for the members only, so you can check out what stuff is there. God forbid if we get sophisticated and figure out what's available and what's not. So that's kind of later. Right now we're on spreadsheet. I think that's all I got for right now. And I do have the excess handbooks and calendars with, if you feel so inclined. I think that's it.
You won't have to take them back.
Yeah, there's that. I was hoping that one person that hasn't responded would have showed up. So be it.
Thank you, Jeff.
Unless one of you is Lee Schroeder, MD. I haven't heard from him and I can't get a hold of him, so.
You have an imager set up there, like we did last time.
Probably.
Take a couple of minutes. Questions asked.
Actually, you got. That's the list.
I got it. Okay. Oh, okay.
Oh, wow.
Yeah, you have to focus on it.
There's a lot of fun stuff on there, some collectibles, some good.
Is this on the website?
No,
Not yet.
it's not. That's what we're kind of working on.
Yeah.
Stick out.
Oh, look, it's off.
There we go.
Okay, yeah, that's some of the stuff.
There you go. And I don't have the Sea Star on that list. Well, I have it on now, but I printed it before. But that's the stuff that we got. I forgot about the image.
This one's probably better.
Okay.
The equipment manager is a person to talk to. And if it says observatory, is who you talk to.
Just to continue here, what they were talking about, some of you remember when we had this with the observatory last year, we had a lot of things we were in there we wanted to check out. This is one of the things they were talking about, the list. And the other thing some of you might remember is we set up this telescope loaner program here just to fill out names in that, so we knew who was taking what. And then there's some times to return and a date in that. And then there's also a quick describes certain problems that arise, who's responsible for damaged equipment, something that happens to it. Yeah, it's something we discussed last year and that, so this is somebody does sign out telescopes or something from us, then through our program, there is some requirements in that too. Okay, the other thing is, we talked about this last year when we did the we're ordering the new Argo Navis, and we had talked with some other companies because Sky Safari was not building that Sky Safari unit anymore. Some of the other companies had stopped production, ServoCat and M2, as they're changing over to the issues with chips and what happened last year. Pegasus Astro came up with the smart eyepiece. We did discuss about possibly buying for the observatory, depending how it worked and designed and everything. Okay. They have come out with that eyepiece, just to let everybody know. You can go to Pegasus Astro, look at the design in that, because it's the one that's being sold by High Point Scientific and AstraZeneca, and 4 or 5 other places are going to start selling it. This is the one that is has its own Sky Safari Wi-Fi power built into it. It'll project the images to your cell phone or tablet and things like that. You'd have to read up on the whole issue. It's worth reading up on. This is right now, they're telling us they're looking at April of 2025 when it become available. So we're going to wait till we see how well these work, what kind of issues or problems there are with them before we go out and spend that kind of money. So, and you think about it, you got a 10 or a 12-inch telescope. That'd be one hell of a sea star. Yeah. One of these.
I
Think about that.
this is a nice solution if you have a Dob.
Yeah.
Push around those things with minimal effort, you can get imaging, some kind of outreach imaging, that kind of thing to happen with very little work. It's a lot of money, but for a good camera, you'll pay that anyways.
Yeah.
That I had a question about the big mount. That's got can that handle 2-inch eyepieces, or has it got a weird?
Yeah.
Okay,
Yeah.
I wasn't sure on that one.
Yeah, we can fit it to the 2-inch adapter and get rid of the 3-inch.
Each about more often, Jeff.
Apparently.
Okay, and the last thing I'm gonna just throw out real quickly that we started talking about, Jim Sledowski probably recognizes this. Some of you will too. This is the article in the Detroit News about the McMath-Hulbert issue. As you can see, the first thing over here talks about astronomy buffs fight to save abandoned observatory. And we get down here in the center, we find quest for historic status reveals split between stargazers and owner. Mr. Kinsler has his own views on how he's going to do this. But if you have someone in your neighborhood that gets the Detroit News, it is 3 pages. It's a lot. Takes some time to sit down and read. I tried to go to a few places today to see if I could get yesterday's paper, and places I had didn't have it. So I don't know. I got these photographs from the library. They had a copy of it, so I sat down and read the copy in the library. Other than that,
It's a, by the way, it's quite a comprehensive article that discusses all the issues and a lot of the history. So if you guys get a chance, I'll try to send that copy to you guys.
okay. Yeah, it is very complex.
Did it mention the estimated price for the property, the article?
It did talk about the old prices, what they paid for it, and what
Yeah, it
Kinsler
did.
paid for it. Yeah.
Or more?
Yeah, that was 30 years ago or 35 years ago.
Yeah.
And I think it was like 250 grand.
Yeah.
I'm looking at Zillow and I don't know if this is accurate. 1.6.
1.6 million, right? okay. Look at inflation. Take 250,000 over 30 years.
I think they putting a bunch of houses on it.
They're not allowed to do that. No, long time ago when I was at the president of DAS, one of our board members was the attorney for rights and way leasing for Oakland County. And he looked into it too, because there's some people thought, oh yeah, I could bulldoze over. He said the way the deed and the title is written up and the way that is structured and set up as a research facility, a scientific facility, and regulated as that, says they cannot do that. They cannot buy that property and doze it and put up condominiums.
That's
This is
correct.
where there's an argument right now between everybody, because there's some people think, oh, that's a good idea. There's other people telling, no, you can't do that because it's written up in the deed and the leasing the way it was done through the rights and way and that. And that's something that's been brought up time and again. And it's something that they've kind of just thrown off at the side, telling them you can't do it. So I don't know what's gonna happen.
Well, we cut the price way down because, you know, the land might be worth 1.5 million, but the property as is.
Right. That's a big argument.
It has been several years since I've been there, but I talked with one of the club people, not the owner. I don't think anybody, has anyone here actually talked to the owner? I never.
I haven't, no.
It
But
was
the
on
people,
TV the other day.
but I guess it's in pretty bad shape. And so you're probably talking 7 figures to fix it up too.
It's true.
It's a whole story. And again, the article is, which is rather lengthy, discusses a lot of those issues. And it would be, if I get down there or if I get up there in May for a talk, we can kind of update you guys on what's going on and what isn't going on and what's real and what's just a bunch of BS.
That'd be worth it. No, that would be good. That would be good. It really would. Okay, on ending this stuff. Turn it back over to Charlie. That's the observatory report.
Thank you.
Oh, and finally, just to let everybody know, new heaters are working. And I've been out there a couple times checking them. And they're still functioning because they're designed that way. You turn them on and you leave them on. You don't go back out and adjust and play with them. That's our thought. The test will come in the next 2 weeks when we hit that -4, that -7 degree. And then we'll know what we're getting. So with that, that ends my report.
Thank you, Jeff. Ken?
So they successfully posted, my wife successfully posted the Ann Arbor Observer. Actually, that's something read it tonight. And she's working on making sure that the topic didn't get in on time, the February talk or time limit. And she's gonna see if she can get that into the online. Other than that, I don't have anything. I am looking for speakers. I have 2 available. I'm not sure when they're this long.
Second time, probably actually.
Oh,
That's, oh, yeah, gotcha.
We had the C-Star available for members to use. We got no members who signed up to use it. So I think it's like the third member to contact me and say it. I mean, use this to borrow this. Maybe we should send that notice to the veterans saying, just get on the list. I'll make you sign it.
Except for the last week's February.
Yeah, when we brought that up, when we were talking about it, we had like 7 people in the room immediately raise their hand. So we'll see where they are.
A little more often in late May.
Yeah, so that's true too. Right now, they might not be too encouraged.
Especially the borrow now.
But right.
I'd love to get us on this too.
Yeah, exactly.
I had a good event at Leslie Park last month. And 8 members show up.
How's that comment?
No, that was foolish. We didn't have. I guess the garage, but sunset was.
Does anybody have anything else? In that case, I'd entertain a motion to adjourn. All right. That's support. All right, thank you very much. See you next month.